Okay, these are the 8.1 notes, which are going to be on polar coordinates and polar equations. Before we get into doing things with polar coordinates and polar equations, it's good just to talk about what the polar concept is all about. Basically, it's another coordinate system. So you guys are used to, up to this point, basically working on an XY coordinate system, whether you've done regular functions, quadratic, polynomial, rational, and so on, or doing even trig functions. Those are still basically all done in a rectangular system. Rectangular meaning coordinates x comma y, right? Polar coordinates are r comma theta. R represents a radius, that's a distance from the origin, which is called the pole instead of the origin. And theta is an angle of rotation, typically in radians. So in a second, I'll walk you guys through it. We'll start out in just baby steps. We'll plot a single polar coordinate. Then we'll do a little bit of coordinate conversion so you can see the connection to rectangular. So it's not gets totally unrelated. They're related. It's just a different system. And then we'll do polar equations and also talk about how they're related to rectangular equations. And really, we'll do that by conversion. So by doing the conversions, you can start to make some of the connections. In terms of polar graphs, which we really won't do until the following section, polar graphs are just the kind of graphs that are basically best done on a polar axis. Why they lend themselves better to a polar axis is because they're very circular in design, and that actually usually works better with the idea of a polar axis. So, it'll build as we go. After you get the first couple days under your belt, you'll get the picture of what polar is all about. Today is like just kind of the basics, really. Like I said, we're going to start with just a basic polar coordinate. Down here is a list of some of the names of the graphs we'll hit in the next section. They've got some kind of funky names, but the graphs are kind of interesting, something a little bit different than what you guys are used to. Here's some actual visual examples. Again, this will be tomorrow. Cardioids, lemnicons, roses, lemniscates, and actually a lot of other kind of funky stuff. We'll kind of graph some of the more common graphs. And tomorrow, or I should say Monday for you guys, but we'll talk about what's the deal with these graphs and how they're generated. But today we're going to start by looking at just polar coordinates. The basic idea for a polar coordinate is that you've got a distance from the pole, which is called your radius. And then you rotate through. If I can get to cooperate here. There we go. So, radius is distance out from the pole. That can be like 1, 2, 3, 4, just about anything. Then rotate through. Let's say it's about pi over 6, maybe pi over 4. So usually what we're going to do is we're going to actually go through an angle of rotation first. Then we're going to travel out along that rotation line, the distance of the radius. You can do it either way. You can do the r first, and then the theta, or the theta first, then the r. Now this will make a little more sense when you're actually on a piece of polar graph paper. And so you guys can just try to follow along your note sheet as you're doing these notes. Okay. So the next thing to do is kind of look at that idea on a grid so we can see what does the polar axis look like. So a polar axis actually does not have a rectangular grid behind it. It's got a circular grid behind it. And the circles represent radius. So if you start with the first circle, you're at radius 1, second circle, radius 2, and so on. That distance is always positive, although your theta can be both positive or negative because, think about things in terms of rotation. You can have a positive rotation, you can have a negative rotation. So as far as where this point is at out here, this black point, well, if I look at it rotation-wise, that's rotating to the pi over 3 rotation line. I'm going out 1, 2, 3. If I was given that a coordinate, that would be 3 comma pi over 3. Now the reverse of doing this, which is totally okay too, is I could actually travel out to the radius 3 circle and then just rotate to pi over 3. I kind of like to do it in reverse. This is up to you guys. I don't really care how you do it, but I kind of like to do the rotation first and then count out along that rotation line. That's up to you guys. So that's basically the idea of the concept of plotting a polar coordinate based on rotation. Okay. Basically, what we're going to do next is just kind of practice. Let's see how many more times I can say basically. All right, so we're going to practice with just plotting some polar coordinates, something kind of simple. This diagram you don't need to do anything with, just sort of looking at it for a second, but just showing you again one more kind of time on going through how these are created. So if this is my rotation line and I'm starting at 0, 3 pi over 4, radius 1. Rotations can be negative, so negative pi over 6, then out on that line 1, 2, 3, radius 3. You can rotate around more than one time, so just like any other time we're talking about rotation, so 3 pi, radius 3. And then there's the idea of a negative radius. This one kind of messed you up a little bit at first, but it's kind of easy after you practice a little bit. So you're going to rotate. This is why I like the angle rotation first, particularly when I got a negative radius, because I'm going to rotate to the pi over 4 rotation line. And then what a negative radius actually means is to travel along that line in the opposite direction. So pi over 4, negative 4. To me, if I do negative 4 first, what does that mean, right? So I prefer to do it the other way around. Again, you guys can kind of choose what you want, but go to pi over 4 and then in the opposite direction, negative 4. So that's the basic idea of a polar coordinate. A couple of quick visuals for you. Let's actually practice plotting. So on your note sheet, you guys have the same examples, and before I start showing you, I'm going to give you a second to just kind of look at it. Try it yourself. Basically, rotate to the 7 pi over 6 rotation line, travel out radius 2, plot a point. So you guys go ahead and try it yourself before I show you. Now this line here is, when you guys get done plotting, put your point down. This line does not belong as part of your graph. That's just my visual for the smartboard or for the notes. But rotation to the 7 pi over 6 rotation line, travel out 1, 2. And there's your coordinate. This should not be actually drawn as part of the graph. Okay. Pretty straightforward, I think. If you guys should all be able to visualize rotation in terms of pi, and the idea of this new axis just being really a circular, where every ring represents a radius. Not that bad. All right. Let's try a couple more. So go ahead and try negative pi over 3 and 4, or 4 comma negative pi over 3. Again, if it's me, I'm probably going to do radius second. So I'll actually rotate to the negative pi over 3 rotation line, travel out radius 4. So take a second to try that on your note sheet. So again, starting my rotation at 0 to negative pi over 3 out 1, 2, 3, 4. Should be a point sitting out there. There you go. Again, this line not part of your graph. That's just me helping you guys visualize. All right, let's try some others. So now with a negative radius. So again, you're going to rotate to the pi over 4 rotation line. This is where I think, again, going radians first, or the angle of rotation first, is better. And then that way I could think of it as, from that rotation line, just travel 3 in the opposite direction. So again, get my rotation line going here. 1 sec. There we go. So pi over 4, 1, 2, negative 3. Yeah, one more time, right? Pi over 4, negative means go in the opposite direction, negative 3, there you are. Okay, so I think polar coordinates is no more difficult than plotting just any old regular coordinate, right? Once you understand how it works and you plot a point, it's pretty simple. And then, of course, a collection of points of a certain type function will give us some of those unique polar graphs, which we'll look at in the next section. Okay, one more, just to kind of talk about variation a little bit. So the idea here is for you to find the original one, of course, and then once you've got that, try to come up with some other polar coordinates that would put you in the same location. So for starters, you want to get this one plotted. So negative 3 pi over 2. So we're going to go negative rotation. Negative 3 pi over 2, and then negative 4, which is going to be here. So one more time, right? Negative 3 pi over 2, negative radius takes me in the opposite direction. So I'm there. The question for you guys now is, now that I know where that point is, can you come up with some other polar coordinates that would put you in the same exact spot, but using maybe a different theta or changing the radius sign on the radius? So think about some other possibilities, other ways to get there. So go ahead and take a second to jot some down. I'll light up some of the answers here in a second. So one possibility would be 3 pi over 2 and 4. So if I did my rotation, positive 3 pi over 2, radius 4, got it. Another possibility would be to go to negative pi over 4, negative pi over 2, excuse me. Radius 4, same location. Pi over 2, negative 4, same location. The only real purpose of that exercise is just for you guys to kind of visualize, what are ways to get to that location using different r, different theta. Okay, that's enough time, I think, on polar coordinates. Actually, I've got one more thing to show you with polar coordinate, but almost done with this. So one more, 2, 2. So when you look at 2, 2, radius 2, and theta 2. Now, we've had this kind of number before in the previous chapters. The idea is, that's supposed to be a radian measure, so where is it? Well, if you think about quadrant, let's start with that. Theta 2 would be in quadrant 2, because you're beyond 1.57, probably closer to pi over 2 than not. If you do a little bit of conversion, about 115 degrees. Now, again, you guys don't necessarily have to convert, but just do your best to get close, approximately in that same spot. So I'm going to rotate about 150, what I think is about 115 degrees, travel out radius 2, plot a point. Radius 1, 2. Okay, so you might get some measures like that. Yeah, no big deal. Just think about quadrant. You don't have to be perfect. You don't have to even do conversion, but I try to think about it as being closer to pi over 2 than to pi, so you're kind of roughly in the right spot. The next thing for us to talk about is converting, and so to convert coordinates from one to the other, polar to rectangular and vice versa, we've got to have some kind of relationship to the two. So I've got the axis laid out for you in terms of x, y, and r. So we got radius in there. Theta is also in there. And the first thing to do is start making some connections. If you figure you got an xy coordinate given to you and you want to figure out what the radius is and what theta is, think about the connection between these things. This is not a new diagram for us. We've had this diagram plenty of times before. You're just talking about the Pythagorean theorem. So x squared plus y squared equals r squared. If I'm given x and y in a rectangular coordinate and I want to figure out what the radius is, I'm just going to do Pythagorean theorem. Also not new for us, going back to the previous chapters, is tangent of theta. Well, tangent of theta based on that sketch is y over x, and it's always been y over x. So the idea is these would become my coordinate conversions. Given a rectangular x and y, I could find the r and the theta. There's only one catch to doing theta, is that you're going to have to pay attention to what quadrant the original coordinate is in. So you choose the theta in the same quadrant. That's important. Okay, let me show you a few problems here. So what I'm going to do with this is actually sort of have the two different grids going at the same time. So when we're done, we can do sort of a visual comparison. Like, is what I got, polar version, really actually in the same location as the rectangular coordinate? They should be in the same location visually. Now I've got the two grids basically scaled to be the same. So for example, like if I was traveling right here, radius 1, radius 2 is basically matching these distances. So when I get done doing this, the coordinates actually should show up to be in the same spot. It's good for starters just to think about where 2, 2, negative 2, 2, would be. If you think about an angle of rotation, before I ever even start this problem, I can visualize and tell you what the angle of rotation is. I'm guessing it's going to come out to be 3 pi over 4. Because I'm in quadrant 2, and if you got a coordinate that's got the same two x and y values, you know you basically are on a pi over 4. Now we're going to double check it, of course, and actually calculate it here in a second. So what you need to do is get your r going, the r calculation going, tangent of theta, and keep track of your quadrant. I'm about out of time on this video, so we're going to pick up on the second video to finish the example and the rest of the examples.